Let's assume we have a function f, and we know that we can find the derivatives of f for any n we want. So we have this is the n derivative of f for all n greater or equal to 1. Let c be a real number, and let's write what is the Taylor series associated to f around c. So f of x is going to be represented by, we are going to have some coefficients an that depend on the derivatives, and then we're going to have x minus c to the power of n, and this is from 0 to infinity. This is going to be true for some interval of convergence, so this I is the interval of convergence. Okay, so when we want to approximate the value of this function at some point in the interval of convergence, we are not going to use the whole series. We are going to use probably some not very crazy polynomial Pn of x, which is going to be just the nth partial sum of the series we have over here. So it's going to be the sum from 0 to n of the coefficients ai x minus c to the power of I. So this is not exactly the value of f of x, but we hope that in some sense this is not too far away when we are considering values of x inside the interval of convergence. Now the question we are going to try to answer in this video is, how far are we when we are approximating a function with a Taylor polynomial? So how big is the error when we use this approximation? The theorem we're talking about is Taylor's theorem, also known as Lagrange form for the error. So we have the function that has derivative of all the orders in some interval centered at c, and then for each value of x in the interval, we write the value of the function at x as the sum of the value of the polynomial plus something else. The polynomial is a Taylor polynomial of degree n, and then this Rn we have over here is what we call the error term. And we have a formula for this error term, and if you look at this, it's not too different than the coefficients we have in the Taylor series we are talking about. So let me write the coefficients because I didn't write them earlier today. When we find the coefficients, we are going to have the n derivative for the n coefficient evaluated at c, where we are writing our expansion, divided by n factorial. That's for any value n. So that means if we were going to write the function as the nth polynomial plus, and we want to write what comes in the next term, the next term will be the one that has an plus 1. So we'll have the function, the n plus 1 derivative of the function, evaluated at c, divided by n plus 1, all of it factorial, and then we'll have the x minus c to the power of n plus 1. So that's what we expect to see on the next step. In this case, the error term looks very similar, and you may need to look at it 2 times to realize that the difference is this value b over here. Everything else is exactly what we'll write on the next term if we wanted to write the polynomial, Taylor polynomial of degree n plus 1. The only difference will be that the n plus 1 derivative, in this case, is evaluated at b, and it just says that b lies between x and between c and x. So let me draw a picture here. Let's say we have our value c. We are inside our interval of convergence, so let's say this is c minus r, and here we have c plus r, and then we have x. I don't know on which side of c is x, but let's say we put it here on the left, and then b is some value that lives in between x and c. So somewhere around here is our value. Now let's keep in mind that when we talk about finding the error of an approximation, we never find the error of an approximation, because if we were able to find the error of an approximation, then well, we'll find the exact value and it wouldn't be an approximation anymore. what we find usually is a bound on the error. So, for instance, we find, I don't know, I'm just making up some numbers. We say that the value of something, A, I'm going to say, is approximately 7. And then we say that the error is an absolute value less than 0.1. So what we are saying is that we don't know the exact value of A, but we know that between 6.9 and 7.1 is our value A, somewhere around there. So the error is going to just give us a bound, and this is what is doing the error term Rn here. It's just giving us a bound because it's not telling us what the value of B is. It's just telling us for some B, this is going to work. And let's see now how we use this to actually find a bound. This is our example. We want to write the 7th degree Maclaurin polynomial for sine of x. And we're going to use the polynomial to estimate sine of pi over 12. And then we're going to use the Lagrange error term to determine an upper bound for the error of this approximation. So I wrote over here on the side the Maclaurin series for sine of x with integral of convergence the whole real line. I just screenshot that from your formula booklet. It's there. So if I want the 7th degree, I'm going to need to write sine of x is x minus, then we have x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial. That's the 7th degree Maclaurin polynomial for sine of x. And we want to use it to approximate what is sine of pi over 12. So that means we are going to need to find what is pi over 12 minus, and then we have pi over 12 cubed over 3 factorial plus pi over 12 to the power of 5 over 5 factorial minus, one more time, pi over 12 over to the power of 7 over 7 factorial. And if we write this in our calculator, we are going to get an approximation. Let me show you how I wrote this sum in the calculator. I could have written by hand exactly what we wrote before, but that will take quite a bit of time, I believe. So I have a sum. I have my value I going from 1 to 4, so there will be 4 terms. The terms are going to be changing sign, positive, negative, positive, negative. So I have a factor negative 1 to the power of I plus 1 to do that. Then we have pi over 12, and they need to get the powers 1, 3, 5, and 7 for that. So I wrote 2i minus 1. So with 1 we get 1, with 2 we get 3, and so on. And then that same value is the one that is dividing everything with a factorial, so 2i minus 1, all of that factorial. When I press enter, my calculator was as nice as to give me the exact form of that, so I can see over there that I have the pi cube, pi to the power 5, pi to the power 7, with the right signs, plus, minus, and then some getting really big denominators. But yeah, wait, I say I want an approximation, so let me press Ctrl Enter to get the approximation. 0.258819. Let me write this down. So my approximation for sine of pi over 12 using the 7th degree Maclaurin polynomial for sine of x, and my calculator is written here to 6 significant figures. Now we want to know how bad this is. So we want to have a bound for the error. We're going to have, of course, an upper bound. That's what makes sense to find. And we're going to use the Lagrange error term. So that means we are going to be talking about the next term in our polynomial. Let me write here. Note the notation on the statement of the theorem that when we are talking about the polynomial of degree n, we call also the error term of degree n, even though we use the index n plus 1 when we write it down. So here we have R7 of x is going to be, we need to take the 8th derivative of the function and evaluate it at some value b over 8 factorial, and then we're going to have x minus 0 in this case to the power of 8. So this is going to be, because we actually are doing this for the value pi over 12, we are going to have the 8th derivative evaluated at some b, and now we can write here that b is between 0 and pi over 12. Yeah. And then we're going to have 8 factorial, and we're going to have just pi over 12 to the power of 8. Now, what is this 8th derivative of the function? Right here, don't have a lot of space, but the original functions of the 0 derivative is sine of x. When we take the first derivative, we are going to get derivative of sine is cosine of x. When we take the second one, we are taking the derivative of cosine, so negative sine of x. And we take the derivative of this to get the third derivative and get that to be a minus cosine of x. And when we go to the fourth derivative, we go back to sine of x. So we have this cycle of 4 derivatives. So for 8, we are going to be back at the beginning of the cycle. So this is actually just the function sine evaluated at some value b, and then again this pi over 12 to the power of 8 over 8 factorial. We want to know an upper bound for this, so we want to know in absolute value this error term R7 at pi over 12. Well, it's going to be the absolute value of the sine at b over 8 factorial. Everything else can be outside the absolute value, of course. Then it's going to be pi to the power of 8 over 12 to the power of 8. But, well, the absolute value of sine of b is going to be less or equal than 1. So this is going to be less or equal than pi to the power of 8 over 12 to the power of 8 times 8 factorial. So that's an upper bound for the error of this approximation. So what we are saying is that the value of sine of pi over 12 is something in between. The value we found as an approximation, so 0.258819 minus pi to the power of 8 over 12 to the power of 8 times 8 factorial, and the value we found as an approximation, 0.258819, plus, again, this error bound we found, pi to the power of 8 over 12 to the power of 8 times x factorial. How big this is? Let's check this in the calculator, what this approximately is. This is 5.47 times 10 to the power of minus 10. So that's actually a very small error because the upper bound is very small. It's of the order of 10 to the power of minus 10. To finish the video, let me just correct something small I wrote in the last line. When we find the upper bound for the error, we say that it's less or equal than the number we found, 5.47 times 10 to the power of minus 10. So it could be that it's exactly that value. So I should write here for the brackets of my interval, brackets that include the endpoints, because I can't really discard the endpoints at this moment.